Everyone. In this video, we're going to talk about software, an agile approach in software architecture design space. Traditionally, many software architectures have been designed using what's called the waterfall model. This approach is a linear process, which means we move step by step without going back to check and or improve what was done before. Imagine trying to build a house without ever double checking the blueprints or making adjustments. Once the walls starts going up, it doesn't allow for much flexibility. So there are many problems with this waterfall model. Number one is no iterative refinement. One of the biggest drawbacks in this traditional model is that it doesn't really focus on iterative refinement. Iterative refinement is when you continuously make improvements as you learn more throughout the project. Without it, you risk getting to the end of the project and realizing things could have been done better, but it's too late and to make any changes. Imagine baking a cake and only finding out it's missing sugar once it's out of the oven and you cannot add sugar anymore. So that's number one problem, no iterative refinement. Then there's problem two, like ignoring key architecture attributes. Another issue is that the model doesn't pay enough attention to capturing key architecture attributes. Think of these attributes like the foundation of your house, things like strength, durability, and flexibility. If we don't clearly define these attributes from the start, we might end up with an architecture that doesn't meet the actual needs of the project. And let's talk about deployment environment changes. These days, environment in which our software operates can change rapidly. Think of a company moving its operations to the cloud, for example. In traditional architecture, it is if the environment changes, we often have to start from scratch, like tearing down an entire house because it doesn't fit in the new neighborhood. The solution to this is iterative agile architecture. To solve these problems, we need better approach, one that is more iterative and agile. This means continuously refining the design and implementation, as well as reusing existing components. Rather than starting from scratch, every time something changes, it's like building with Legos. You can easily rearrange or add pieces to suit the needs of the moment without rebuilding the entire architecture or structure. Let's dive into how we can go from project specification to working software architecture through a more modern iterative approach. The step one is proposing the high level architecture. When we begin a project, we start by creating a high level software architecture. This is like drawing a rough sketch of a building. You know what rooms you need, but haven't figured out how the electricity or plumbing will work yet. At this point, the design is abstract and doesn't consider specific deployment issues, like where the software will eventually run. Step two is identifying key attributes. Once we have the basic architecture, we identify key important attributes for each element and connector. Think of these attributes like key features of your house, the materials, the size, the strength of each part. For example, we might define how a database should communicate with a web server or the connector, and the server should be capable of the element, what the server should be capable of. Step three is refinement with deployment constraints. As we move forward, the architecture goes through several refinements to meet the actual deployment constraints. For instance, if the software will run on the cloud, we adjust architecture accordingly. This is like adjusting your house design to fit the landscape it's being built on. So there are some unique features of this approach, that is delayed binding of connectors. One unique aspect of this approach is something called delayed binding of software connectors. This means we don't lock in how parts of the system will communicate until later in the process. It gives us flexibility to make better decisions as the project evolves. It's like deciding where to place doors and windows only after you have seen the natural lights in the house. And another key feature is the seamless integration of multiple architectural styles. Different part of the system might require different designs, just like how different rooms in a house may have different layouts or purposes. For example, one part of the system might use a client server style, while another uses peer-to-peer architecture, but they all work together harmoniously. In agile approach, we gradually build a complex software architecture by integrating multiple styles. This results in a system similar to today's web architecture. The diagram below shows how we can refine a design step by step using specification attributes to meet design goals. For example, imagine designing an architecture to present data from a database to the client. Initially, it is simple standalone application serving data to a single user. As the system grows, we refine and extend this design to meet new requirements, much like modern web systems. Let's look at this design example where the client graphical user interface module or GUI module communicates with a data retrieval and processing module. First, the GUI module collects data retrieval criteria from the user and displays the selected data in a visual interface. Meanwhile, the data retrieval and processing module retrieves the necessary data from the database and pre-processes it based on the user's criteria. These two modules are designed to run in separate thread within the same process, allowing for efficient multitasking and smoother user experience. Let's say the requirement specification changes, and now the application needs to serve over data over the internet to multiple clients. In this case, the connector between the client GUI and the data retrieval and processing module must change. It has now a new network attribute, meaning it will handle communication over the web. All clients will be using the same software to access the data server, allowing for a consistent user experience. To implement the networked connector between the client graphical user interface and data retrieval and processing module, we can use remote method invocation or RMI technology. If both modules are written in Java, we can use Java RMI. If they are in Windows, we can use Microsoft.NET remote invocation. In both cases, the connectors is one initiated, meaning the client starts the communication. It's also networked and signature based, ensuring the modules can communicate reliably over a network. Now, if we want to support third-party client GUI devices, we need more flexibility in how the data is represented and handled. Since we can't control the technology used by the third-party clients, we will use a message and protocol-based connector. This will allow the client and server to communicate regardless of the client's implementation. To achieve this, we use HTTP over the TCP/IP network. The client sends a request and receives the data in flexible format, with the server handling everything. For customizable data presentation, we use HTML to specify how the data should be shown and allow the client to send requests to the server through HTTP. To support flexible data presentation, we introduced two tiers for data handling: server-side data presenter tier, and the other was client-side data presentation tier. Server side, this is managed by the HTML generator module on the server. It dynamically creates the HTML files based on the data requested. And the client side, this is handled by the HTML presenter module. On the client side, it takes the HTML from the server and renders it for the users. These two tiers work together to ensure that the data is presented flexibly and efficiently, adapting to both the server and the client's needs. To handle significant data processing on the server, we use a divide and conquer approach, splitting the server-side architecture into three tiers: presentation tier, business logic tier, and data source tier. The presentation tier responsible for generating HTML files and handling how data is presented to the client. Business logic tier, this handles the core data processing and any business-specific rules or calculations. And finally, the data source tier manages the data storage and persistence, retrieving a document or databases records as needed. By separating these concerns, each tier can focus on its role, making the system more scalable and efficient. When we apply the layered architecture style to the design, HTML generator, and data retrieval and processing modules, our system mirrors a typical web architecture. In this setup, the server-side presentation tier acts like a web server responsible for generating HTML. The business logic tier functions like an application server handling data processing. Together, they form a structure very similar to standard web architecture, providing a clear separation of concerns and scalable design. This is the end of chapter 2, software architecture design space.